So now our next speaker today is not Kashaev, and he will speak on Taimur spaces. No.
It's written there.
No, I will say. So I will talk. My subject now will be very different to yours talk, but it will be motivated by three-dimensional possibility. I'm happy. But essentially it will be more analytic. So my title is Quantum Boundary. And LCA rules. So LCA group is a locally compact abelian group. But before going into this subject, let me just start the motivation. Motivation comes from TQFT in3. But often constructing TQFT is not a simple problem, and there is a simpler version of halfway towards this goal, which is just representations of the mapping class. Representations of groups. So let me gamma G n. So this is the mapping group of S G n, genus G n removed points. As I wrote yesterday, this can be thought as a set of connected components of the orientation preserving homeomorphism group. But there is one particular case, gamma 0 n, which can be identified with a break group of, I guess, n-1 strings. So if we remove just one point from a sphere, it will be a real plane, and then the remaining points will correspond to strings. So in that sense, Valery gave yesterday talk about representations of that group in the algorithms of three groups. Here I will talk about representations in Hilbert spaces. And there will be some algebraic construction which allows, once you find realizations of these algebraic constructions, you can get corresponding representations. And the motivating example for break groups comes from the beginning of quantum topology, which allows to construct the representation of break group out of R matrices, which are solutions of the Yang-Bax equation. So let me recall what is an R matrix. So let V be a vector space, and let us take R an invertible linear transformations of its tensor square. Then we say R is an R matrix if we have it satisfies a Yang-Bax equation. Which looks like, for example, we can write it in this way: R tensor identity of V composed with identity V tensor R identity tensor V equal to identity V tensor R identity V tensor R. Non-linear, three-linear equation for R. If it is inversible, then we get. Then there is a theorem. I don't know what is the right attribution to it, but I would say that this is a Jones to Rife, which tells that as soon as you have a solution, as soon as you have a R matrix, then you have a representation of any Bn, given R matrix. R matrix. Then there exists representation rho n, which is a R matrix R. Then rho Rn, a homomorphism from Bn to automorphisms of V power n, which is canonical, which sends sigma I if Bn is given by Artin representation. Then sigma n, sigma I is sent to identity V power I minus 1 tensor R, tensor identity V power n minus I minus 1.
What is rho? What is element of this?
Rho is a homomorphism. So this is a representation.
In what sense it is canonical? So you.
In the sense that no matter what the value of n is, you just write these matrices acting in the nth tensor power, and you have a representation.
Why not to say simply that consider the following homomorphism and write down this formula?
Yeah, you can say it differently maybe. Is not it clear what is the statement?
No, for me it was not very clear. It was canonical, but it is given by exact formula, right?
Yeah, but maybe not canonical. I just wrote there exists a representation such that
So the claim is that there is such a representation, which on the generators gives this. So we need to, it is compatible with the relations. That's the point.
But what is nice thing about this theorem is that you don't study all break groups one by one. You just solve algebraic problem just in a given vector space, not knowing of any break group, and then once you've done this, you get representations to all break groups simultaneously, based on this single algebraic object. And based on that theorem, so the natural question is that is the following. So can one have similar theorem for any mapping class? To have some simple enough algebraic object that would allow to make a any mapping class group, any of any genus, any number of points. So, and the reality, as far as I know, there are many answers. And I will give just one particular, which is rather restrictive, but still interesting. So one answer is the following. One answer is as follows. Again, vector space. Vector space. We have one element in the automorphism group of vector space, and another element in automorphism group of its square, with relations. A cube is identity in V, first relation, third order element. Second, pentagon identity for T. So I'm using new notation. Here T12 is T tensor identity V, T23 identity tensor T, T12. This is more tricky. The 213 is more tricky to write out, but you can say it this way: P12, P13, T23, P13, where P is permutation. Permutation, which what it makes to pair of vector UV, it just exchanges their places in a vector space too. So we have this. So this is written again in the tensor cube of the vector space V. So similar to this equation. And one more relation is of mixed type, which tells that T12 A1 T21 is equal A1 A2 P12.
Which is A1 and A2?
Yeah, so A1 A1 is similar to. So this is in automorphism of V tensor V. This is in automorphism of V power 3. Okay, so then A1 means that it acts in the first component, A2 acts in the second component, A tensor identity, A2 is identity V and A, and T12, so T12 is just T. In that case, we can just erase, right? This is not informative, but T21 is conjugation by the permutation. P, T, P. Yes?
What index of permutation means? P1.
Index also you can, yes, you can remove it. Yeah.
And when you write P13, it's P13, T23, P13.
Yeah, so let me put it this way. 1, 2. So 2 will be replaced by 1.
And P12, it's just P.
P tensor identity. Yeah.
Okay. Thank you.
So this is some notation used often in multilinear algebra. So this is not linear algebra; it's multilinear algebra. So this brings some difficulty. Otherwise, it is just a first-year algebra course, linear algebra. But what we add this word multi, which means that we deal with tensor products of many different spaces.
Excuse me,
Yes.
the second relation, right hand, it contains 3 letters?
Not only two. Only two. Yeah, it's a five key
It's
in total.
different from the young box.
From the young box is different. Yes.
Okay.
So if I ask Google multilinear algebra, I get some such letters.
I'm not sure.
But for most students, they only learn multilinear algebra because they fail the course one time and then they have to take it again. So it's
Oh, I see. That's another meaning. But the multi means bilinear for maps,
Yeah.
trilinear, multilinear maps. That's what corresponds to multi. Okay, so that's algebraic structure. Then we have a theorem. We have a theorem. Then given such pair AT, get rho in the homomorphism of gamma Gn, but m should be negative, positive, gamma n into automorphism of v some power for n strictly positive. Yeah, let me be more precise. For some n, and if 2g minus 2 plus s is positive and s is positive. And this n actually is 4 times, I think, 4 times this. So they're pretty much similar to that theorem, but one remark, which makes things rather different and this system to be very restrictive, that V is necessarily infinite dimension. One can just show that there is no solution in finite dimensions for this system.
Can you say something about values on generators?
Yes, such that that's more difficult because we need a presentation. And presentation is based on ideal triangulations of the surface. And then, okay, let me omega AI is sent to identity V power, tensor identity V power corresponding, so we suppose that we have a linear order. And now, okay, alpha I and omega ij is sent to AI Tij. Let me just explain what is alpha I omega j. So we think of surface decorated ideal triangulation. What is this? So we have a linear order in the set of triangles I. Okay, I enumerates these triangles. Each triangle has a marked corner. And then, so for example, S11. Then we have this decorated ideal triangulation. So this is identified with this identified with opposite side. So torus with one puncture and the corner, and then we have two triangles, and then what makes alpha I? Alpha I just shifts the marking of the corner in the i's triangle. So rho I changes marked corner to anti-clockwise, replaces the star to the next corner. Because if we change, then we get another ideal triangulation, and this operation we call alpha I. And then omega ij is
Wait a second, it should be an element of the mapping class group, right?
yes, but this is a little bit more way to mapping class group. So I will spend a little time on that. So for the moment, this is the story of pairs of ideal triangulations, and with little difference. Like here, the difference only in one triangle, with the placement of the star. Here's the difference in two triangles which share one common edge, and the diagonal is shift like this. And let me just, because this wasn't my purpose, this kind of answer to your question. Last year I think I explained this when I was in September here, but
Who remembers? Lift your hand.
Let me just say the general fact. Given a group freely acting in a set, group G freely acting in a set X, then there exists a canonical connected groupoid GXG with object set, objects xg given by G orbits and the morphisms given by G orbits in the Cartesian square of X, and vertex group G. And the description is very simple. So you see, objects are just elements of X in brackets with the so they are the equivalent. Okay, so this is equal to Gx for any G, and morphisms are given by pairs of elements of X, and they are equivalent by diagonal action of the group, and this belongs to home set of class of X and class of Y. And the composition is simple: XY composed with UV So to be able to compose, we need that the orbit of y is the same as orbit of u. So there exists a unique group element which brings u to y. Equal y. And then you can erase y. X, G, V. That's a property. And now, if we go back to this picture, then the set X is a decorated ideal triangulations of our surface. Group G is a mapping class group, which freely acts on the set of decorated ideal triangulations. And these pairs represent morphisms in the group. So implicitly, we have a mapping class group sitting as a vertex group associated with a given triangulation. I'm sketchy here because this wasn't the purpose of my talk. This was the motivation.
The talk begins now, yeah?
Yeah, we can say so. Because for me, what is important.
Now you want to solve these equations.
Yes.
Okay, but the interesting part for us is to understand them. Okay.
Okay, so the motivation is this system. So, and due to remark here, it can be only infinite dimensional.
So what is where these equations come from? So the
They are very nice. They are very nice graphical interpretation. So this is clear, right? If you do it 3 times, this is clear. Okay, let me draw a few pictures just to describe that the relation very natural. Very natural.
Можно на доску побрызгать.
Ага.
Скажите, пожалуйста, а вот вы треугольник нарисовали, вы подписали угол, идеальный угол, да, написано, там посмешно отсвечивает. Вот.
Просто отмеченный угол выделен.
Выделенный угол, ага, понятно, спасибо.
Чисто комбинаторно.
Они все идеальные, может, там все вершины идеальны.
Да, я понял, а я вот...
Ну, один из них тоже хочет отметить.
Слушай, ну смотрите, спасибо.
Написано маркет кода.
Это им позволяет определить операцию А.
Там не ро, а альфа. Okay, so what I was going to do now?
You wanted to explain the relations.
Yes. That's a simple.
Graphic.
Yeah, graphic explanation. Yeah, so we take pentagon and triangulate it like this. Well, 1, 2, 3. But they can be ijk. Then just look at the picture which defines omega ij. So I put omega 1, 2. Then I don't touch this triangle, but I change this diagonal to the opposite one, and the mnemonic rule is simple. You just rotate it clockwise, pushing all the symbols accordingly. You get to here. Then you can do the same thing with 1, 3. So I'm using all the details of the decoration. So the stars should be placed as they are. So I don't touch 2 because it is omega 1, 3.
Are you sure? If you rotate this, that's not what you get. The star should be at the top corner, no?
I just drag it.
Right.
Then this stays.
Oh, this is not affected by the twist?
No, you see, what happens here?
Oh, I see. Okay,
so
okay.
so
Okay.
you just rotate it and push all the symbols.
But you don't twist the symbols. The
No,
marks,
no.
you don't twist them.
No. Just a smooth operation
Okay.
like this. And then now I'm going to do this, here, the same thing. Result here, this star stays here, and this one here, and 1, 3. Now I can do omega to 3.
It's better to do, that was right hand side. It's better to do the left hand side.
Yeah, but it will be in the one picture, the both.
Um,
One. That's a final picture. And let us start here from omega to 3. And omega 1, 2 brings immediately to the same.
I don't understand why the T23, T12. So first, who goes first?
Yeah, so you should read like in fundamental group composition.
Oh, so for operators the same.
Yeah, yeah. So just omega 1, 2 times omega 1, 3.
You delete once.
In the groupoid, I also use this. You see, this thing coincides with.
But you know, for linear maps usually.
Yeah, I agree. But this is always a headache, the order of composition.
Well, that's why it's multilinear algebra.
Okay, so this is pentagon, and this relation is very nice, also graphically. Maybe I should show it here. So we start from here with omega 1. Then we can apply alpha 1. And then you can see clearly that we can apply omega 2, 1. And now, how it is written relation? Yeah, so we have, then here we can apply alpha 1, alpha 2. And then here we have just P1, 2. And the claim is that this set of relations is enough for realizing any mapping level.
So all triangulations
All
ideal are
yes.
related.
Yes.
Basis. And no other relations.
No. Just permutation group relations, which I implicit.
But this is only for surfaces with at least one
Which are
ideal,
triangulizable. I mean,
which have one point, ideal point.
yeah.
So yesterday you explained
Yeah, this is
closed.
just the initial stage of a new project for closed. Yeah.
Mhm. So maybe we also need to fix something and then it might work. Mhm.
Say again, what is the statement? So such this pentagon identity?
Yeah, so like this I translate into these relations.
Yeah.
And the claim is that now just a pure algebraic statement that by associating to those operations, geometric operations on the triangulations, those operators in the tensor power of V, I am able to realize represent the mapping class group. And the homomorphism of the mapping class group in the GL of that big space.
Now, this is a mapping class group which may permute the ideal points, right? So it's a
Yes,
big
yes,
one.
yeah, this is no problem with computation.
To realize
In particular, Brane groups are represented by this system.
in order to realize mapping class group, yeah, I more or less understand, but here you have identity, yeah? What is what relation of identity to realization?
What do you mean, identity here? Or
Second, for example, T12, T13.
Yeah.
It says if you can find such automorphisms A and T that satisfy these identities,
Yeah.
then they will induce a homomorphism from the mapping class group
Yeah.
to some matrix group.
but operator, V, remember, V cannot be finite dimensional.
Yeah.
So it will be some operator representation.
Operator representation of the mapping class group. Yeah?
Yes.
Okay.
How much time I spent on that?
Less than half an hour. So,
So my that was motivation. Okay, so that's the reason why I am interested in this system. And I would like to. So remember again, it can be only infinite dimensional. So the rest of my talk will be more functional analytic than linear algebraic, because one has to deal with infinite dimensional vector spaces.
maybe smelly.
Okay, but
If we are brave, we do not differentiate from infinite dimension.
But still continuing motivation, well, let me briefly describe what quantum Teichmüller theory gives as a solution. So, what gives quantum Teichmüller theory as solution? So, when I say quantum Teichmüller theory, that means we take Teichmüller space as a symplectic space with very Peterson symplectic structure, and then using physical methods, we quantize it. Which means for mathematicians this is a scaring thing, but in reality you pick up nice coordinates in the symplectic space with simplest possible Poisson brackets with respect to symplectic structure, and then you replace them by operators in a Hilbert space, and simultaneously you are able to realize symplectomorphisms, at least part of them, as automorphisms of the corresponding non-commutative algebra. And eventually you end up with unitary operators realizing these transformations, and which preserve also the algebraic relations. And here I will just give the answer what is the outcome of this was the content of my lecture, September lectures. So I just give
We have a very small intersection here between.
how the solutions look like. But A is not interesting. I will not talk about A. Just I will show the structure of T. So so V is equal. V is a L2 space of a real line, and Heisenberg operators which is called P hat and Q hat, act on the functions as follows. Q hat acts on a function of the real line as a multiplication operator. This is simple. And P hat acts as a differentiation operator, but with some normalization factor which I fix right away. But since we are in L2, so the functions can be not differentiable, but these are non-bounded self-adjoint operators, so they have their own domains of definition. So they don't have to be defined on any vector of the Hilbert space. They have to be defined on the subspace which is dense in the Hilbert space. And that means that, for example, the domain of P should be differentiable functions with the derivative being in L2, square integral. While the domain of Q, this should be L2 functions such that multiplication by X still gives the L2 function. Okay, so these operators, and then T is given by the following explicit formula: 2 pi I, P1 hat, Q2 hat, a certain function of one single operator argument, Q1 hat minus Q2 hat plus P2 hat. And psi is very special function, where psi is of x is equal, this is just notational fact, which is the inverse of certain special function called phi b of x. B is a parameter, and it is very explicit spatial function.
Now you explain one solution of this system.
Yes, just one. Phi b of x is equal to exponential 1/4 integral along the real line slightly shifted upwards, sinh of b z, sinh of b inverse z, dz over z, t minus 2i xz. Well, b here can be, is supposed to be a positive real number, quantization parameter.
So for every b, you have a solution.
Yes. It's a family of solutions. So,
Okay.
and that's it. So everything else is written.
Wait a second. Q1 hat. That's an operator.
Yeah. So this is in
So what does it mean?
endomorphism of L2 of R2. Is it an analog of tensor product V tensor V?
So how you apply psi?
So Q1 hat acts on a function of two arguments, right? X, Y. So it acts like Q in the first argument, X, F of X, Y. Q2 acts like Q on the second argument. Y f of x, y. And likewise, P. P2 differentiates y.
Now, how you apply psi to this thing?
Yeah, so it is the
Psi is a function, right?
well, so in functional analysis, you easily define operators of operators
So you diagonalize, apply to all
and then act
eigenvectors.
on the eigenvectors.
And if you can't diagonalize,
But these are self-adjoint diagonal.
self-adjoint, so you can always
So
diagonalize.
the function should be defined on the spectrum of the operator on which it is evaluated. So you use spectral theorem. So the function so the Hilbert space becomes functions on the spectrum, square integrable, and then this acts as a multiplication operator on the
And this the second factor e to the power.
Likewise, yes. So it is a
It's the same.
function exponential of this self-adjoint operator.
So
Which is much
basically,
simpler.
you compute on every eigenspace separately,
Yes.
one-dimensional eigenspace separately.
But what is important here, the composition, because this doesn't commute with this, but the composition, this is unitary operator, this is unitary operator, and composition of unitary operators is well defined. It is again a unitary operator.
Wait. But is it true that each such operator preserves the eigenspaces?
No.
Because
This is just a,
then you diagonalize.
okay, let me just, given self-adjoint,
Oh, because there are two.
yes,
That's why.
self-adjoint operator, A, okay, A hat, and a function with spectrum of A, part of the real line,
Mhm.
okay, spectral theorem, and then for any f which is defined on the spectrum of A, generally C-valued, we define f of A, which acts, which is a f of x, spectral projection
Mhm.
of x
Okay.
integration along that spectrum.
Okay. And now this big phi, well, some incomprehensible.
Yeah, so this operator, its spectrum is a real line, because it's self-adjoint, easy to show.
Mhm.
So any function defined on the real line will give will define this operator.
And it has real values, this function. It is-
No,
it is complex.
it is on the unit circle. So phi b of x, phi b is a function which sends real line to t, unit circle,
Yes.
unit circle.
Okay.
And in particular, that means that this operator is unitary.
That's a unitary operator. And
Unitary.
The other one also is unitary.
This is also unitary, because the spectrum of this product is
So you get a
Again,
unitary
right?
operator. So
Yes.
T is unitary.
yeah. So the result T is unitary.
Okay. Maybe you should realize that for most people present, this formula, this integral is fully incomprehensible. I mean, some will probably understand all the science there. So can you give us some kind of intuition about this integral? So where it comes from?
No, it is technical. So this was I spent 8 lectures last year on explaining this function.
Okay. So it's just.
So it will
like-
just accept. I mean, for the rest of my talk, this is not important how it comes.
Okay, but where it comes? Can you say it, two words from
Yes,
what
quantum.
science? From the theory, quantum technique.
Yes. You just calculate. Just step by step.
Some incomprehensible computation leads
Yeah.
to some incomprehensible.
But what is important here is that it's properties of phi which are crucial, and there are just few of them. And the first is that it takes values on the unit circle. Right? So let me just give the list of properties of it.
Is it what is called quantum logarithm?
Yes, this is Kashaev's the quantum logarithm, because there are many.
Remember, you had a joint paper with Faddeev on this
But
subject.
not on that.
Not on that. So there is Faddeev's quantum logarithm and there is Kashaev's quantum
Yes,
logarithm.
yes, you can say so.
Okay.
And now properties of phi b of x. The first property, unitarity. So phi b of x, absolute value is 1 for any x in R. Second property is inversion relation. Phi b of x, phi b of minus x is a constant e pi I x squared for any x in R. And zeta is some complex number of absolute value 1. Actually, if you put x equals 0, you see that it's just square of the value of phi at 0. But not very important what is the value of it. And the last thing is most important, is the 5-term relation, which underlies the 5-term relation for t, which is written in this way: phi b of q equal phi b of q, phi b of p plus q, phi b of p. PQ are just the same operators. Now this is in L2 of R. So no double argument anymore. Like for T, everything boils down just to operators acting in the Hilbert space of functions of on one single variable. But multilinear algebra allows to spread it out to multi-component tensor products. And remember that phi, because of this property, phi of evaluated on self-adjoint operator is always unitary. So this is perfectly defined identity for unitary operators in the Hilbert space. And essentially, this list of properties are used for defining a notion of abstract notion of any quantum dynamic. But what I'm going to do to replace the real line with self-adjoint, in the sense of Pontryagin, locally compact abelian group. And all the ingredients in the definition will make sense due to existence of Haar measure on the LCA group. So you will have square integrable functions on that LCA group, and you will have the analogs of Heisenberg operators due to
unit abelian?
Abelian, yeah.
Abelian.
Self-adjoint, but self-adjointness is important.
Group is a group. The group
So
is
the Pontryagin dual should be isomorphic to itself. For example, we know that the group of integers is Pontryagin dual to T unit circle. So it will not fit into this scheme. It has to be self-adjoint. But if you take direct sum of a arbitrary locally compact abelian group with its Pontryagin dual, then it is canonically self-dual. And then you can make sense of this definition. And just since I have to stop, I think, just publicity for tomorrow's lecture, I'll give a very simple example which fits into this definition. And as a consequence, it will give a solution for T and A. and eventually will lead to another unitary representation of the mapping class group. But instead of this complicated integral, there will be very simple function. So all this can be generalized to any self-dual LCA group. Example. LCA group A. Sorry for using the same letter. A equals Z plus T. And the phi of N T. Right? If we want, it should be function on that. So it will be one integer argument, one periodic argument, and here we are. So everybody understands what is the function, because
there is no B.
No B. Just one single, and it satisfies all this, including operator, identity, which replaces
It gives some infinite dimensional representation
of the mapping class.
of all mapping class groups.
And even I can say what it corresponds to. It corresponds to normal curve on the surface, function surface.
Okay.
And also of normal surfaces in normal curves, just curves running on the surface.
So corresponds to, there is only one such thing, right?
Yeah, only one. So this Z roughly counts number of intersection points of the normal curve with the edges of the triangulation. And
so you fix a triangulation, right? You have a triangulation.
Yes.
And
Yes.
this determines somehow such representation, and you can explicitly compute it. Okay.
If you go tomorrow, yeah?
No, I will not talk about interpretation. No, I will talk about how one can write as a solution. No, my purpose is modest.
More integrals.
Little bit integrals, yeah. But the message is that so this solution formalizes pure classical thing in the context of surfaces and puts it in the framework of quantum theory within this scheme.
Okay, so let's send the speaker. And there was a lot of questions, yeah? Some other questions? Yeah. Well, the case it will, many questions will be tomorrow. When I say that normal curve, what means that is some normal with respect to triangulation?
Transversal to triangulation.
Transversal to triangulation.
Not only transversal, it is not allowed such returns. Let's say,
No?
So coming to
Yeah, but you can isotopy them, right? So you up to isotopy.
Yeah.
because
Like if you have triangle, you have something like that.
yeah, this subject, majority of the participants know the subject, and also parameterization of normal surfaces by some.
But maybe I will say tomorrow a few words how this comes out from this.
Yeah, it was very